Well, welcome to the second session of second day of our session in differential operators in commutative algebra and algebraic geometry. Today, our first speaker is Iván Pan from Universidad de la República, who's going to speak about on isotropy of a polynomial derivation into variables. Okay, go ahead, Iván. Thank you.
Thank you very much. I would like to thank the organizer, especially Luis and Jack, for the invitation. It's a great pleasure to be here. And well, let us start. Let K be an algebraically closed field of characteristics 0, and the K derivation that is a linear map which satisfies the Leibniz rule. And the note, like here, of the subgroup of the automorphic group of the polynomial ring, consisting of elements we commute with the derivation. As Daniel explained us last Friday, this is called in general the isotropy of the derivation, because correspond exactly to the isotropy of the action of the group, of the automorphic group of polynomial on the vector space of derivation. Okay. Let us give a first example here. Consider D to be a locally nilpotent derivation, that is, that for any polynomial, there exists a positive integer such that an nth power of the derivation annulates this polynomial. This is a locally nilpotent derivation. So D is conjugate to a derivation of this particular form. This is a result, a classical result, already classical, by Rensselaer. This is valid only for two variables. For example, in polynomials of 3 variables or more, this is not true, this result. No? It's only for 2 variables. And then, if you take 2 derivations which are conjugated with respect to an automorphism of the polynomials, then their isotropies are conjugated too. And then, since in this case, the derivation is conjugated to a derivation of this form, for a straightforward calculation, we may verify that the automorphisms in this isotropy are disjoint. The isotropy is conjugate to a group of this form, where the automorphisms, I write automorphisms in this form, like a pair of polynomials, fg. Here, f is a linear polynomial, an x, and g is gamma y plus a polynomial in x. It's a very particular, very special form of the isotropy in this case, with an additional property related to the polynomial a here, which defines, in fact, the derivation. We deduce, for this case, or this example, that the isotropy is not an algebraic group in this sense, does not act as an algebraic group acting with respect to the natural action, is not an algebraic group. That is, if you think which is not an algebraic group. An algebraic group is an algebraic variety. Then, if we say that a subgroup is an algebraic group, if it is an algebraic group, like a subgroup of the polynomial automorphism of the, we say that the isotropy is not an algebraic group if the action of the group in the polynomial ring is not represented as an algebraic group. That is, it's not an abstract algebraic group in such a way that the action, which is a map or defines a map like that, is an algebraic map, morphisms of variety.
Iván, there is a question from Guillermo Cortiñas.
Yes.
Should gamma also be non-zero?
Non-zero, exactly. Excuse me. Yes, yes. Alpha, gamma is non-zero. Okay, then I repeat. You say that an algebraic, a subgroup of the group of polynomials, of the automorphic group of polynomials, is an algebraic group when it is an algebraic group abstractly, and the action of this group, in particular of the isotropy, on the plane, on the affine plane, is a morphism of varieties. And then in this example, one may see that, in fact, the isotropy is not an algebraic group. The reason is because an algebraic group is an algebraic variety. Then it depends of a finite number of parameters. But here, one sees that this group depends of a polynomial, which is arbitrary. And then it depends of an infinite number of parameters. That's because the degree is not bounded. And then in this example, one gets that a locally nilpotent derivation admits a non-algebraic isotropy. The aim, in fact, of this talk is to prove that the converse is also true. That is, a derivation of the polynomial ring into variables is locally nilpotent if and only if its isotropy is not an algebraic group. Well, let us give a sketch of the proof. Assume that the isotropy is not an algebraic group, and then let us prove that the derivation is locally nilpotent. As we said, but for the example, for the present example, in fact, may be generalized, and it is a result by Kambayashi, that if a subgroup of the automorphic group of polynomials, a subgroup like that, for example, like the isotropy, is not an algebraic group, then the elements here in this group are given by polynomials, two polynomials, fg, where f is phi x and g is phi y. And then the fact that this group is not algebraic may be translated in the following form. These polynomials are bounded degree, are not bounded degree. Non-algebraic group implies that degree of f and g not bound. For the group, okay, that is for any integer D, this group contains an element of degree greater or equal than D. This is the case. Then we introduce now an invariant with respect to conjugation of the derivation, which is explicitly the number of D-stable principal ideals generated by an irreducible polynomial. If you think of D as a vector field, for example, in the case where the field is the complex number, then these vector fields correspond to a foliation, and a principal ideal stable under D generated by an irreducible polynomial corresponds in this geometric setup to an irreducible curve which is tangent to the foliation. Then this is the interpretation, the geometric interpretation of a principal ideal which is stable for the derivation. And consider two cases. When this number is 0, that is, there are no such a D-stable principal idea, or there exists one at least. In the first case, one may prove that the isotropy is finite. It is a consequence of a result by Gael Cousin, Luis Gustavo Mendes, and myself, that in fact study in this paper, we studied the birational symmetries of a foliation, and then this works in the complex case. But one may generalize the situation in the case of derivation to prove that in fact the isotropy is finite, even in the case where the field is arbitrary. And then we are in the case where this number is different from 0. In this case, we denote by capital E-T such D-stable ideals like that, and we are assuming that this set is different from 0. And then first, suppose that this number is finite. In this case, if you take an isomorphism here, in the isotropy, the fact that this element commutes with the derivation implies that these automorphisms permute the stable ideals. Then we have a homomorphisms in the set of permutations of this set, the set of the stable ideals. Under this hypothesis, this set is finite, this group of permutations. And then, since we are assuming that the isotropy is not an algebraic group, the kernel here is neither. Okay, because it's not an algebraic group, in this case signifies that into the isotropy you find elements of arbitrary degree, automorphisms of arbitrary degree, and then the same property holds for K. But K here, by definition, is the set of automorphisms that fixes principal ideas like that. And then, in this situation, we may use a result by Blanc, Jeremy Blanc, Emmanuel Stamfli, a result which classifies automorphisms, in certain sense, classifies automorphisms, which stabilizes curves, and explaining how these automorphisms belong to an algebraic group, something like that. And then we may deduce for that such elements, such the polynomials, the reducible polynomials defining the stable ideals, at an special form. There exist an automorphisms such that transform f to a polynomial in one variable. With this property, then one may do explicit calculations. And then, for example, the derivation may be written like that. And then d applied to f is a f prime, and this is a multiple of f, then a in fact belongs to K. And with that, we may continue like that, and then finally, since the degrees in the isotropy tend to infinity, the degrees of the polynomials defining the isomorphisms, the corresponding isomorphisms, of course, tend to infinity, then one deduces from that in fact a is 0, and then b is a polynomial in X, as we wanted to prove, more or less. It's only a sketch. Let me see the time. Nice. Now we consider the other case where this number, the invariant, is infinite. That is, there is an infinite number of these d-stable ideals generated by reducible polynomial. So, under this hypothesis, d vanishes on a non-constant rational fashion. This is a classical result by that book. Old, very old. It's 79. Using this result, then we have two situations to consider. First, if this rational function is a polynomial, in fact, then one may assume that the kernel of the derivation is a polynomial ring where the variable is f. The fact that the isotropy is not an algebraic group, that is, has no bounded degree, implies that there is an automorphism such that applied to f belong to a polynomial in one variable. It's more or less the situation as before, The second case is where f is really a rational function which is not a polynomial. Here is not, here is wrong. It's not a polynomial. Okay, In this case, G minus alpha H is the stable for any alpha. This is a calculation. When a rational function is zero under D, this is the same that the pencil of curves defined by F, G, and H is constituted by these stable elements. And once again, the fact that the isotropy is not an algebraic group implies, in this case, that the curve here, the curve defined by the element, the generic element of the pencil, is a rational curve for a generic alpha. Okay, and then in these two situations, one needs to work a little more in order to obtain the results. For example, in the first case, one works more or less as in the preceding part by using the result of Blank and Stanford, and prove that f, the polynomial f here, may be, no, excuse me, here in fact, what I prove is that since the polynomial may be assumed to be a polynomial in CAD X, it depends only on X, then Y uses that the kernel is stable by the elements in the isotropy. This isomorphism stabilizes this polynomial, and then one needs to calculate, do some calculation in order to verify that in fact the only possibility is that the derivation being locally nilpotent. The second case is more difficult, in fact, but one needs to use birational geometry. And get first that the isotropy may be embedded into the so-called the Jonquière group, and then work into the Jonquière group to prove that in fact the only possibility is that D being a locally nilpotent derivation. A final example to show that in fact this theorem is not true for 3 variables or more in general, because this example may be generalized to the general case of 3 or more variables. Then this derivation, where there is a polynomial which depends only on Y and B also, then D, capital D, induces a derivation D in Ky, which is non-nilpotent if the degree of B is greater or equal than 0, clearly, because you apply D several times and then it's never 0 here. And then capital letter neither, because capital letter is an capital, excuse me, capital D is an extension on D, and then if D is not locally nilpotent, then capital D is not locally nilpotent. But it is easy to verify that these automorphisms, or an automorphism of this form, belong to the isotropy, where PZ is an arbitrary polynomial. And then, once again, this is not an algebraic group. Okay, and this is the idea. Okay, thank you very much.
Thank you, man.
I will finish. I don't know. Yes, questions.
Okay, are there questions for Iván? Maybe one question.
may I ask?
Yes.
In the, can you go back in the slides?
Okay. Excuse
Because
me. Yes.
it was something about, go back at least two slides back.
Here?
No, before. Yeah. But okay. So in the case, let me see. Let's go one more to the next one. Yeah, here, I mean, how is it obvious that? Do you mean df is? I mean, you are acting as is f were in k of x, not phi of f, or did I get things completely wrong?
You ask about that? If this is not.
No. So you say d of f is af prime because you are assuming that f is a polynomial in one variable.
Yes.
Yeah. Or do you mean d of phi of f? Or
excuse me. Yes. You are right. No, in fact, yes. Okay. Here is at least of d is 5 minus 1. D is the conjugation.
I see. Okay.
You may conjugate, use these automorphisms in order to conjugate the derivation in such a way that now the polynomial which is stable is simpler than the other one is that.
And then in the infinite case, when you reduce to the case when the kernel of D was K of F, yeah, and then the calculation you did later on, because then you explained how you proceeded in the case one, right? Yes.
More or less.
So yeah, but then I mean, the fact that F is in the kernel of D, right?
Yes.
So if you do D of phi F, it's the same as phi of df, which is 0.
Yes, exactly.
So phi of f is constant, and so f must be constant because phi is an automorphism.
Yes.
No,
excuse me. No, phi is f. No, but phi is a change of variables of the curve f equals 0. That's because phi of f is not 0.
No, but d of phi no, but d phi f is 0.
Yes. D of phi f, yes.
Yeah, sorry for interrupting, but it's time for the next talk. Whether we continue this conversation after.
Okay, sure.
No problem. Or maybe on the forum.
Okay. Yeah, thank you.
Thank you.